This is the fourth lecture of work energy theorem, work energy, power and collision. Okay, so in this lecture we'll solve from question number 137 to question number 140. All of the questions are more or less conceptual in nature. So try to see or try to grasp the concept, especially questions regarding spring, how is spring energy stored, and spring energy is a conservative force, and how they are applied. Okay, so let's see. In this question, what the question says is that there is a ball, okay, connected by a string. The length of the string is L. What the question is saying is that what is the minimum velocity that must be given to this ball such that this ball completes the circular path, okay, completes a circular path around this center or around the center where the string is tied. Okay, now see, for the circular path, for any object to complete a circular path, the minimum velocity should be given such that at topmost point, okay, at topmost point, the connecting force means if it was kept in top of a rod, okay, then normal contact force, it is connected by a string, so out here tension force, the connecting force would be equals to 0. Okay, so out here make a note, for the ball or object to complete a circular path, to complete a circular path, the connecting force means either tension or normal, whatever is the connecting force, the contact force, instead of connecting force let's write contact force. Contact force at the topmost point, at the topmost point, should be equals to 0, should be 0. Okay, the contact force at the topmost point should be equals to 0. Now let's check out here, the velocity out here is v, it goes out here and velocity at topmost point becomes vt, let's say vt. Okay, so let's analyze this topmost point. Okay, so out here, okay, what are the forces out here? The forces out here is mg and t. The tension forces already became 0, so if we analyze the force out here, okay, so at the topmost point, mg is equals to mass into centripetal acceleration at topmost point, okay, at a means at this position a. Okay, mass and mass gets cancelled, so g is nothing but centripetal acceleration, where centripetal acceleration is equals to v square by r, or v at topmost point by r. Out here the value of r in this circle is nothing but the distance l. See, r is equals to l. Although I drew a improper circle out here, just imagine to be a proper circle with center to be this one and radius to be l. Okay, let me draw the proper circle so you all get a notion of what's happening out here. So out here this is, okay, now it can be more like a circle. Okay, so out here velocity at topmost point square is equals to under root of gl. Okay, so velocity at topmost point is equals to under root of gl. Okay, so the condition for minimum velocity such that it completes the whole circle is nothing but condition at topmost point is equals to, or velocity at topmost point is equals to under root of gl. Now my question is, what should be the velocity out here, or what should be the velocity at bottommost point? Okay, so can I evaluate this point and this point? So I'm applying work energy theorem between these 2 points, the top point and the bottom point. So when I applied work energy theorem, the final velocity is out here. So final kinetic energy is nothing but half mvt square minus what is the initial kinetic energy? Half mv square. Half mv square is equals to what are the forces doing any work? The only forces doing any work out here is gravity forces. The tension forces are zero work. Why? Because the elemental displacement, okay, all discrete the ds, the displacement, okay, is always perpendicular to the tension force. So the work done by tension force is zero throughout the circular path, okay, and work done by gravity force is nothing but m minus of mgh, where h is nothing but twice of radius, or 2l. What is vt? Vt is nothing but under root of gl. So vt square is nothing but gl, or if I rewrite this equation, half mvt square is nothing but gl minus half mv square is equals to minus 2 mgl, okay, or out here, okay, 2 mgl plus half mgl is nothing but 5 by 2 mgl is equals to half mv square. What I did out here is I took this minus 2gl and send it to the left hand side, and I took this minus half mv square and send it to the right hand side. So if I evaluate this, v is equals to under root of 5gl. So the minimum velocity out here, the minimum velocity at bottommost point through which the particle must be projected so that it completes a whole circle is nothing but under root of 5gl, under root of 5gl. Now the question is asking, with what minimum velocity has the point of suspension to be shifted in horizontal direction for the ball to move along a circle about that point? So the velocity, minimum velocity should be under root of 5gl for the ball to move in a circular path. The second part of the question is saying, what will be the tension of the thread at the moment it will be passing through the horizontal position? That means when the ball is out here, when the ball is at the horizontal position, okay, what is the tension out here? What is the tension in this ball? Okay, so let's say velocity at horizontal position is equals to vh. Can I apply similar position or similar kind of equation? T is equals to m vh square by r, okay, or tension force is equals to mvh square by r. Problem is I don't know what is vh. Similarly, I apply work energy theorem between these 2 points, between horizontal position and the bottommost position. So if I apply work energy theorem, half mvh square minus half mv square. What is v? V is nothing but root 5gl. So what is v square? V square is nothing but 5gl is equals to what is the work done by gravity force? Work done by gravity force is nothing but minus mgl, minus mgl, okay. So outer m and m will get cancelled, okay. Half vh square minus 5 by 2 gl is equals to gl, or half vh square is equals to, if I send the 5 by 2 to the right hand side, it would be gl plus 5 by 2 gl, and 1 plus 5 by 2 is nothing but 7 by 2 gl, okay. So out here I made a little bit of mistake out here. I haven't calculated this minus out here. See, minus mgl. So I forgot to take the minus out here. So here it would be minus gl. Okay, let's rectify this. Minus gl. Okay, so out here instead of 7 by 2 gl, it would be, if I send this minus 5 by 2 to the right hand side. So 5 by 2 gl minus gl, or 5 by 2 minus 1 is nothing but 3 by 2 gl. Okay, 2 and 2 will get cancelled, and velocity at horizontal position would be 3gl. or velocity at horizontal position would be under root of 3 GL. So velocity at this position VH, okay, VH, velocity at horizontal position would be under root of 3 GL. One more thing, velocity at this point would also be under root of 3 GL by symmetry, okay, but in downward direction. But that is of another question. Now the question is asking what is the tension of the thread at the moment it will be passing through horizontal position. So what is the tension in the thread out here? The tension in the thread is nothing but tension force is equals to mass into centripetal acceleration, but centripetal acceleration is equals to Vh square by r, where Vh is nothing but under root of 3gl. So tension force is equals to mass into 3gl, which is equals to Vh square by l, or tension is equals to 3 mg. So the tension force out here is equals to 3 mg. Okay. What we study out here is the generalization of last two problems. Okay. Study of vertical circular motion under the effect of gravity. Under the effect of gravity. Okay. So basically, we'll summarize this in three particular categories. Okay. So basically, here are three circular orbits. That means this mass or this bob out here, okay, tries to move in a circular orbit. There are three kinds of questions out here. The first type is what is the minimum velocity at the bottom so that it completes a circular orbit. The second type of question is what is the minimum velocity so that this pendulum reaches the topmost point. Okay. And the third kind of question out here is what is the minimum velocity so that this bob reaches the topmost point, okay, or completes the circular orbit. The only difference in the third problem or in the third case, different from first two, is in the first two I have used strings or rope, okay, whereas in the third case I have used a massless rod. Okay, this is a massless rod, and attached to this massless rod is a pendulum or a bob. Okay, so in the first case, the question should be arranged in such a way: minimum velocity to complete the circular orbit. That means this bob will stay in the circular orbit throughout the motion. Out here, minimum velocity to reach the topmost point. That means what is the minimum velocity that should be applied out here so that it reaches the topmost point. Out here, the minimum velocity so that it reaches the topmost point of circular orbit. Okay. In the first case, okay, the minimum velocity to complete a circular orbit, out here what will happen is the contact forces, okay, either the tension forces, okay, if it's a circular path means the outside is a roadblock or some kind of ramp, okay, then the normal forces. To complete the circular path, the condition is the contact forces at topmost point, okay, either normal force or the tension force. The contact force at topmost point would be equals to 0. Normal or tension is equals to 0, okay, and there is mg out here, gravity force is acting, okay, but mg is equals to vt square by r. Then what do? We apply work energy theorem between this point and this point and get the minimum velocity to be under root of 5gr, 5gr, where r is the length of the string or radius of the circle. Okay, any point in the circle, just apply the simple method. The net force is equals to mass into centripetal acceleration, okay, and apply work energy theorem between this point and this point or any other point that is asked in the question, okay, or change in kinetic energy is equals to work done by all the forces, and out here only gravity force does some work. Why? Because contact forces are directly perpendicular to the displacement, so the work done by contact forces out here is equals to 0. In the second case, however, okay, when the question is asking find the minimum velocity to reach the top, out here I must apply minimum velocity so that it goes out here, okay, the string will break the circular path out here. That means the tension will become slack out here, or the contact forces would become zero out here. Then it would follow a parabolic path to the topmost point, okay, and then again it will return to its parabolic path, and then again it would continue in a circle. So for this type of question, what is should be the minimum velocity at topmost point? The condition out here is nothing but velocity at topmost point should be equals to 0, okay. So if we apply velocity at topmost point is equals to 0, I'll get v minimum out here, okay, and I can simply apply work energy theorem between this point and this point, okay. So if I apply work energy theorem between this point and this point, I'll get v minimum is equals to under root of 4gl. Now the third part of the question, when instead of being attached to a string, it is being attached to a massless rod, okay, that is glued to a massless rod, the condition for it to stay in a circle, okay, the minimum velocity for it to stay in a circle is also the necessary condition for this bob to reach the topmost point. That means what? If I apply a minimum velocity out here such that this bob reaches the topmost point, it will automatically stay in a circle. Why? Because doesn't matter out here, the normal contact forces cannot be zero, no, because the mg forces is acting on the normal contact forces. Out here what should be the maximum c, since it is already not breaking off out here. So suppose it contains some kind of glue or some kind of thing that has some strength, so that, okay. So another variation of question would be what should be the maximum allocated value of this ball or this pendulum bob so that it does not fly off at the topmost point, okay. It do not have to fly at the topmost point. See, it will always break. See, if this glue or if the glue has some strength, suppose some strength, the velocity at the bottom will always be greater than the velocity of the top, okay. So whenever it has to fly off, it will fly off at the bottom, no. So the only type of possible questions out here is what is the minimum velocity of this ball so that it completes a circular orbit. All I'm saying is the condition for completing a circular orbit and the condition for reaching the topmost point is same out here. Okay, if it reaches the topmost point, it will complete a circular orbit where Vt is equals to 0. And when we apply work energy theorem between this point and this point, you get the minimum velocity should be under root of 4 gl, okay. Similarly, in the second part, at what point or at what angle does it break the contact, or does it leave the circular path? When contact forces is equals to 0, that means when tension forces or normal forces is equals to 0, it breaks the circular path, okay. But these are the three variations of the same questions. Out here what the question is saying is that a particle out here, okay, is tied to a string and it is given a velocity v naught. So it will wrap around this disk, and while wrapping around this disk it follows this path, okay. The question is asking how long will it move along the plane until it strikes the cylinder. That means the time taken to strike the cylinder. I have to find out the time taken to strike the cylinder, okay. See, can I deduce one thing? What is the total forces acting on it, acting on this particle? The only force acting on this particle is the tension force, okay. And during every point in its motion, okay, the tension force would always be perpendicular to the velocity, okay. So the tension force is always perpendicular to the displacement. See out here, if I draw a straight line out here, okay, the displacement would be in this direction. If I draw a straight line out here, the displacement would be in this direction. The tension force is always perpendicular to the displacement, okay, in the entire orbit. So when a string wraps around a cylinder, the tension force, okay, is always perpendicular to the displacement. So observe out here, the tension force is always perpendicular to displacement or elemental displacement. Okay, and what does it say us? That the work done by tension force is equals to 0. Okay, so if work done by tension force is equals to 0, the kinetic energy of this particle won't be changing, no? Understood? So throughout this entire motion, okay, the particle will have the same velocity v naught, same velocity v naught, same velocity v naught, same velocity v naught. Okay, throughout the motion, the particle will have the same velocity because there is no forces doing any work. Understood? Okay, there is forces that is changing the direction of this velocity vector, but that is there is no tangential forces that is actually changing the magnitude of this velocity, because no forces is doing any kind of work out here. Understood this much? Now all we need to find out is what is the length of this path. Why? Because time is equals to distance by speed. Okay, and since the v naught does not, the magnitude of v naught does not increase or decrease, so speed is constant. Now I need to find out what is the distance of this path. Okay, if I find out the distance of this path, I can simply divide distance divided by velocity, sorry, distance divided by velocity, which will give us the time, because speed is equals to distance by time. I just reciprocated time out here and speed out here. Understood the concept that I'm trying to do, or approach I'm trying to do? Now to figure out the length of this path, I have to take an elemental path length around somewhere. So let's see, when this bob or when this pendulum reached out here, okay, say this pendulum reached out here, the string would have coiled by this much. Okay, so let's say the string has coiled by this much and the pendulum reached out here. Okay, that means the string is coiled by this much. Okay, so let me draw an angle out here and let me draw an theta angle. Okay, let this be angle theta. Now what is the length of this string? From this point to this point, what is the length of this string? Okay, the initial length of the string was L naught. After it coiled up till here, okay, the length of the string is nothing but, see, the entire length of the string, this plus this much amount of coil, is nothing but the total length of the string L naught. Okay, so if we subtract L naught minus this much length, we'll get this much length of the string, and this much length of the string is nothing but L naught. Okay, what is it? That is the total length of the string minus r into theta, where r into theta is nothing but this much length of the string. This much is understood? Okay, now the second part is I need to take another element. Let's check after this point. Okay, it moved little bit forward, or ds out here. This is ds. Okay, elemental displacement. So let's draw a tangent from the circle to elemental ds. Okay, tangent from the circle to the elemental ds goes somewhat like this. Okay, if we join this portion, okay, if we join this portion to the center of the circle and make this angle d theta, okay, can I say this ds, this ds is equals to this length into d theta? Now we'll say why. Okay, see, if this angle is d theta, okay, this angle is so small that this angle can also be approximated as d theta. Check d theta. Okay, let me give you an example. Suppose in a circle I'm drawing a tangent out here, tangent out here. Okay, so this is radius, this is velocity vector, radius 1, velocity 1. Now I make angle 90 degree with radius 1 and make it equals to r2, radius 2. Okay, and velocity is always perpendicular to radius, and this is v2, v2. So if I say the angle between r1 and r2 is 90 degree, can I also say the angle between v1 and v2 is 90 degree? Of course. And it doesn't work for only 90 degree, it works for all degrees. If I simply say out here, this is r2, okay, r2. If angle between r1 and r2 is theta degrees, angle between v1 and v2 is also theta degrees. Okay, that means if r1 or r2 rotated by theta to, sorry, r1 rotated by theta to become r2, v2 has to be rotated by theta to become, sorry, v1 has to be rotated by theta to become v2. The same concept is applied out here. Okay, if this angle is theta, angle between this vector and this vector is also theta. Okay, now how do I write the relation between ds, this length, and theta? Can I simply write ds, elemental length, is equals to L minus R naught into d theta? And how did I arrive at this relation? ds is equals to r d theta. You obviously know. Okay, ds is equals to r d theta, where r was nothing but length of the path, r was nothing but length of the path, d theta is nothing but d theta out here, and ds is nothing but elemental length. And we have to integrate this ds is equals to r minus r theta into d theta. ds is equals to L naught minus r theta into d theta. From theta is equals to 0, see, theta is equals to 0 to theta is equals to some value when it wraps around this cylinder. Okay, so let's say theta is equals to some value, let's point it with red. Okay, to this value of theta, to this entire value of, or this entire value of theta. Okay, let's name this x. Now the question I have is, what is the value of x? Okay, so recall the element of fundamentals. Okay, what is a radian actually? Radian is nothing but the ratio of arc. Suppose I'm telling theta radians. Okay, theta radians. Theta radians is nothing but ratio of length of this line, ratio of arc is to radius, or ratio of arc by radius is nothing but theta in radians. So what is the ratio of this entire arc, okay, divided by radius? This x in radians, understood? And what is the length of this entire path? The length of this entire path is nothing but this length of the string. The string will collide out here only when the entire length has been exhausted. So the length of the entire path is L naught, and radius of the cylinder is already r. So this entire value of x out here, x is nothing but L naught by r. Understood? So out here x will be replaced by L naught by r. L naught by r. Okay. So this x is nothing but L naught by r out here. X is nothing but L naught by r. Now just have to do elementary integration out here. Okay. If I do the elementary integration, let's see. If I integrate this function out here, it is nothing but L naught into theta minus r theta square by 2. Okay, r theta d theta is nothing but r theta square by 2. The limits are 0 to L naught by r, and out here the limits would be 0 to s, where s is the entire length of this path. Okay, because I've integrated for this elemental ds, throughout this path. So the length of this entire path would be s. So out here, if we apply the limits, s is equals to L naught into L naught by r minus r by 2 L naught square by r square. Out here, r and r would get cancelled, and L will become L naught. So if I, or S is equals to, out here if I write, S is equals to L naught square by R minus L naught square by 2R minus L naught square by 2R. If you take L naught square by R common, it is 1 minus 1 by 2. Or S is equals to L naught square minus 1 by 2 is nothing but 1 by 2, 2R. Okay. So the entire length of this path is nothing but L naught square by 2R. So what is the time taken? The time taken is equals to L naught square by 2R, which is the distance, and speed. Speed is equals to V naught, which is same throughout the path, divided by V naught. So this out here is the answer, or time taken to wrap around the cylinder. Okay. Now in this question, what the question says is that this is a spring. Okay. This line you see the out here is a spring that has a spring constant K. Okay. A body of mass M, a body of mass M was dropped from height h. Okay. And at the bottom at B, a sleeve is kept. That means something to catch the mass A. Okay. Now imagine a spring is there. Okay. Somebody is holding a ring. Okay. A heavy ring with mass M out here at height h from the B. And when the ring is dropped, what will happen? The ring will come down and strike at point B. And when it strikes down, what will happen? It will elongate the spring. Understood? The question is asking, find the maximum elongation of the spring after this M has collided with point B. Okay. So what will happen out here is, after dropping down from height h, okay, when it collides with the sleeve, when this body collides with the sleeve, it will extend the spring. It will extend the spring by distance x. Okay. The question is asking, find out the value of this x. Okay. How do I find out the value of this x? So can I apply work energy theorem between this point and this point? Sorry, between this point, okay, and the last point. Okay. What is the velocity? What is the initial velocity when the person was holding this ring of mass m? 0. So velocity out here was equals to 0. Okay. Now as it collided out here, it collided with some velocity. Now see what the string is doing. The string is stretching in downward direction, but it is applying a force to this mass m in upward direction. No, so out here the mass m is deaccelerating. Okay, it will deaccelerate till the velocity becomes 0. Okay, so at the bottommost point, when the string has fully stretched, the velocity of this mass is equals to 0. And after that, what will happen? It will come to, or it will try to go upward. Understood? Okay, this is the point you must understand. While holding the ball, or while leaving, at the instant of leaving this ring, the initial velocity was equals to 0. At the end point, okay, at the final stretch of the spring, when the string is fully stretched, the end velocity of this ring is also 0. Okay, now I can simply apply work energy theorem. A change in kinetic energy is equals to work done by all the forces. All the forces. Okay, so final kinetic energy. Final kinetic energy is how much? 0. 0. What is initial kinetic energy? Initial kinetic energy out here is also 0. Is equals to work done by all the forces. What are the two forces doing some work out here? From out here to H, M, G, H. Okay, where M is the mass of the ring. And will gravity force act along this path? Of course, gravity is also present, no, while the string is being stretched. So plus mgx, plus mgx. And how much is the work done by spring force? The spring force will only act along these two paths. Okay, along this path. And work done by spring is nothing but minus half kx square. This formula you have learnt in classes, and k is nothing, minus is nothing but the spring force acts opposite to the direction of displacement. Okay, now when you solve this one, we'll get the value of x. See, or 0 is equals to mgh plus, let me write this properly, okay, minus half kx square plus mgx plus mgh. Let's multiply this entire left hand side by -1, right hand side by -1. Okay, so if you do that, the signs out here will change. We can obviously do that in mathematics, no? So out here this minus would become plus, this plus would become minus, and this minus would become, sorry, plus would become minus out here. Okay, now see, this is nothing but a quadratic equation. Okay, ax square plus bx plus c is equals to 0, the form of quadratic equation. Out here a is nothing but half k, okay, b is nothing but minus mg, and c is nothing but minus mgh. And the roots of quadratic equation are nothing but x is equals to plus minus, you all know the roots of quadratic equation, no? Minus b plus minus under root of b square minus 4ac by 2a. You have learned this in mathematics. Okay, what is minus b, or the elongation of the spring out here, is equals to minus b. Minus b is nothing but minus of mg. Okay, so if I just substitute the values of a, b and c from this equation, I'll get somewhat like this. Okay, let me write the equation. So we'll get a equation in this order. Okay, this is nothing but b, b, a and c. C, minus of c and minus of c, b square minus 4ac, no, this minus and this minus will become plus by 2 into a. Okay, so when you simplify this, our this equation would come out. Okay, now what I'll try to do is I'll try to take mg square common from these two terms. Okay, I'll try to take mg square common from these two terms. So when I take mg common from these two terms, our equation would be somewhat like this. Now can I take this mg out of the square root? If I take mg out of the square root, it would become somewhat like this. Now can I take mg common from these two parameters, first parameter and second parameter? Now what I'm simply doing is I'm taking k out here. So our net elongation of the spring is equals to mg by k, 1 plus minus under root of 1 by 1 minus 2 kh by mg. In this question, what is being said is that there is a block of mass m out here. Okay, and there is another block of mass m. Okay, these two mass m are connected by a rope. Okay, now this mass m is connected to a string out here and a spring of length L naught out here. The spring constant is given as k. Okay, now the question is saying, if I burn off or if I cut off this string, what will happen? This mass m will start sliding towards right. Okay, at certain point, what will happen? The block m will lift off from the ground. Why? There is a component of spring force in upward direction, there is a component of spring force in left direction. Okay, so the component of spring force in upward direction will try to pull this block upward. Okay, the question is saying find the velocity of this mass m when the block A leaves off the ground, or find the velocity of block A when this block A leaves contact from the ground. Okay, so after a certain while, what will happen? The spring force will become somewhat like this. Okay, and this block M will go down. Okay, so I'm drawing this diagram, or after some time what will happen, that diagram out here. Okay, after some time what will happen, the spring force will lift off from the ground, and this is the tension out here. This is another block of mass m. Fair and fine. The spring force will be nothing but in this direction. And what is the value of spring force? K into x, where x is the elongation of the spring. Asha. Downward force, there is a gravity acting downward. There is a gravity acting downward. Tension force is acting in this direction. Tension force is acting in this direction. Are there any other forces? See, beginning when the block started moving, there was a normal contact force. But when the block just left the contact from the surface, no, the value of normal contact force is equals to 0. So out here normal contact force is equals to 0. Understood? Now you have to find out what is the velocity out here. What is the velocity at this point? Okay, when this block projected up or left the contact of this surface. Can we apply work energy theorem out here? Where work energy theorem states that change in kinetic energy of the bodies is equals to work done by all the forces on the body. All the forces on the body. Now a body in study out here would be this body and this body. And by constant motion, you can simply say that if this block has velocity v in this direction, this block will have velocity v in downward direction. Simply a case of constant motion. So let me apply work energy theorem of this block and this block. Okay. So initial kinetic energy of both the blocks. Initial velocity of both the blocks is equals to 0. So initial kinetic energy is equals to 0. What is the final kinetic energy? Final kinetic energy is half mv square plus half mv square. So 2 into half mv square. Okay, that is the final kinetic energy. That means when this block reached out here, the kinetic energy of this block out here plus the kinetic energy of the block B down somewhere out here, both moving with velocity v. Why? Because they are connected by a string, and by constant motion you can simply say that if this moves with velocity v, this will also move with velocity v downward. Okay, so this is final kinetic energy minus initial kinetic energy. What is initial kinetic energy? 0. Both the blocks were at rest. Okay, is equals to work done by spring, okay, plus work done by gravity plus work done by tension plus work done by normal. Work done by normal force. See, work done by normal force is 0 out here, no? Because displacement is always perpendicular to the normal force. So even if I write work done by normal out here, you can simply say it to be 0. Now what do we need to figure out is the work done by spring, the work done by gravity, and work done by tension. So first let's start with work done by tension. See, suppose from head to head the displacement is x. Okay, x. That means from the displacement of B from head to head would also be x, no? So B would also move downward by x. Okay, okay. Now see, the work done on block A would be plus T into x. Why? Because tension force and displacement are in same direction. Whereas work done on B would be minus T into x, where T and x are in opposite direction. That's why minus. So plus Tx minus Tx. So total work done by tension force is equals to 0 out here. That is why in some books it is written total work done by internal force. Okay, so tension is considered out here as internal force because the positive work done by this tension force will cancel out the negative work done by this tension force. Understood? Now there are two parameters left. Work done by gravity. What is the work done by gravity out here? 0, because the displacement is always perpendicular to the force of gravity. What is the work done by gravity out here? mgx. mgx. Okay. Work done by spring. Work done by spring is nothing but half k into delta L square, or minus half k delta L square, where delta L is nothing but the elongation of the spring or change in length of the spring. Okay, work done by spring is always minus half K into delta L square, where delta L is nothing but the elongation of the spring. Understood? So this equation you have to calculate to find out the net velocity out here. Fair and fine. Now I have two parameters out here. What is the value of delta L and what is the value of X? Okay, see, for that we take this diagram, get final position. We take this triangle. Okay, in this triangle, just let me say, if this is angle theta, okay, then by parameter this line and this line are parallel. So if this is angle theta, this is also angle theta. Okay, or you can simply apply the logic, theta, this would be 90 minus theta, 90, so this would be theta. Doesn't matter which logic you apply. If this angle is theta, this angle is theta. And let's draw the spring force. So upward force out here is spring force. Component of spring force in upward direction is K into delta L, not K, K into delta L cos theta. Okay, out here the horizontal component of spring force would be K into delta L sin theta. Okay, and out here the block didn't stop. The out here the block has some velocity, and as the body goes forward the velocity will change. So out here I cannot say T is equals to or T is equals to this component of force. Okay, out here this body has some amount of acceleration, so we won't go into that much. We'll balance out the vertical component of force. Okay, downward is mg. So when the body just leaves the surface, I can easily say the vertical component of acceleration is equals to 0. Okay, see, you might say, sir, if the horizontal component of acceleration is not 0, why is the vertical component of acceleration 0? Just assume at the beginning of the motion or at the beginning of the vertical motion, okay, what will happen? The body will just start to slide off. That means acceleration is very less, no, or equivalent to 0. So you can take this vertical component of acceleration to be 0. Okay, out here the body already moved so much, so out here horizontal component of acceleration is not 0, but at the starting the vertical component of acceleration can be 0, no? So let's analyze the vertical component of force. Okay, K into delta L, vertical component of force, vertical component of force. Okay, K into delta L, but K is the spring constant, delta L is the elongation of the string, into cos theta is equals to how much? Mg. Okay, this is the first equation that we get. Now see, the length of the spring is given as L naught. Okay, what is the relation between L naught and X if I know the angle theta? Can I say tan theta is equals to X by L naught? Okay, tan theta is equals to X by L naught. So from triangle diagram, from triangle diagram, this is the value of L naught. Okay, this line out here is written as L naught. This line out here is written as X. Let me write out the X. Okay, and let this line be Y or some other value. Okay, this angle is theta. This angle is theta. Okay, can I say X by L naught? Tan theta is equals to X by L naught. So tan theta is equals to X by L naught, or X is equals to L naught tan theta. What I'm doing out here is I'm writing everything in terms of L naught and theta, all the length in terms of L naught and theta. So this X will be L naught tan theta. X is nothing but L naught tan theta. L naught tan theta. Similarly, if you write the hypotenuse, okay, hypotenuse into cos theta is equals to L naught. So hypotenuse is equals to L naught by cos theta, or L naught by cos theta is nothing but L naught sec theta. So this hypotenuse is nothing but L naught sec theta out here. Okay, so this length is L naught tan theta, this length is L naught sec theta. Fair and fine. Now comes the more important part. What is this delta L? The change in length. See, imagine carefully. The initial length of the spring was L naught. The initial length of the spring was L naught. The final length of the spring was L naught sec theta. Okay, the final length of the spring was L naught sec theta. So what is final length minus initial length? Delta L. Okay, so out here delta L is equals to final length minus initial length, which is equals to, or let me write out here, delta L, which is equals to final length minus initial length. What is the final length? L naught sec theta. What is the initial length? L naught. So delta L, or change in length of the spring, would be L naught into sec theta minus 1. Understood? So I got two values out here. First one is delta L. Delta L is nothing but L naught into sec theta minus 1, and the second one is x. Out here x is nothing but L naught tan theta. Okay, see, you will get very confused by all the equations and substitution. Just remember a simple formula. The main equation I'm applying out here is simply work energy theorem. Change in kinetic energy of the body is equals to work done by all the forces. Now analyze the various forces and find out by using which variables you can find out which equation. Okay, these are nothing but just playing with equations. Okay, and you have to figure out how to play with equation in the question itself. The concept I applied is simple. Out here physics ended. Okay, from here onwards, all I'm doing is I'm playing with equations out here. Okay, so out here I got L naught tan theta, out here I got L naught sec theta, and I need to find out L naught or delta L out here. So delta L is nothing but L naught sec theta, L naught sec theta minus 1. Now if I rewrite this equation in proper manner, I'll get K into L naught sec theta minus 1, which is nothing but delta L into cos theta is equals to mg, or K L naught into what is sec theta? Sec theta is nothing but 1 by cos theta minus 1 into cos theta is equals to mg. Now if I multiply this cos theta by this inside the bracket, I'll get 1 minus cos theta. So I'll get K L naught, okay, 1 minus cos theta is equals to mg. Okay, so let me rewrite these parameters out here. If I rewrite this, or 1 minus cos theta is equals to mg by kl naught, 1 minus cos theta is equals to mg by kl naught. Okay, and cos theta is equals to 1 minus k by l naught. Now in normal problems, what I would advise you to do is substitute all the equation in terms of variable, or solve all the problems in terms of variable, and at the end substitute the variables. Okay, but in this problem I would suggest you to find out the value of theta, or substitute the variables out here only. Why? Because the value of cos theta will become so much complicated, and out here you have to find out sec theta, which is 1 by cos theta, and sin theta by cos theta. So it will be more cumbersome if you don't do it out here. Okay, so in this problem, specifically to this problem, I'd suggest you to solve or apply the value of theta, or apply the value of mg, k and l naught in the question itself. So what is the value of mg? M is something, okay, mass of the bar, which is not given. G is acceleration due to gravity. K is nothing but mg by l naught, or 5 mg by l naught. So k out, or k out here, irodov uses x, I am using k. Okay, where k is the spring constant. K is nothing but 5 mg by L naught. So out here I'll use K as 5 mg by L naught. K is equals to, let me erase this one. Okay, so K is equals to 5 mg by L naught. Okay, out here this L naught would get cancelled, mg and mg would get cancelled. Fair and fine. So 1 minus cos theta would be equals to, or 1 minus cos theta would be equals to 1 by 5. Okay, see. So 1 minus cos theta is equals to 1 by 5. If I bring cos theta to the right hand side and 1 by 5 to the left hand side, cos theta is equals to 1 minus 1 by 5 equals to 4 by 5. Cos theta is equals to 4 by 5. Okay, now I need to find out two more values. One is sec theta, other is tan theta. So suppose someone gives me a triangle. Okay, let me erase this part. Let me erase this part. Or let me write out here. So someone gives me a triangle out here where the angle is theta, and I'm given cos theta is equals to 4 by 5. So base by base by hypotenuse, which is cos, is nothing but 4 by 5. If you apply Pythagoras theorem out here, okay, 4 square plus some unknown square is equals to 5 square. So 5 square minus 4 square is equals to this square, or 25 minus 16 is equals to 9 square, or under root of 9 is 3. Now see, I got everything else. I got sec theta, I got tan theta. Sec theta is nothing but hypotenuse by base. Okay, so sec theta is nothing but 5 by 4 out here. 5 by 4. And tan theta from this triangle. Tan theta is nothing but 3 by 4. Tan theta is nothing but 3 by 4. Okay, now I'll solve this entire equation in the next page and find out the value of velocity. See, again to recap what I did out here. I just applied work energy theorem is equals to, work change in kinetic energy is equals to work done by all the forces. So normal and tension forces are already 0. Work done by gravity is equals to mgx. Work done by spring is equals to minus half k into delta L square, where delta L is nothing but change in length. Now to find out change in length, I came to this diagram. Okay, I made any angle theta out here. Then I applied Newton's law of motion out here, vertical component of Newton's law of motion in this block. Okay, and the vertical acceleration is equals to 0. So I made one more equation out here, and I got the terms of L naught and sec theta, means other two terms in terms of L naught and theta. Okay, and then what I'm doing is I'm resubstituting all these terms in this equation. So what I'll be doing right now is solve this equation on the next page. Okay, so if I solve this equation out here, I would get something like half into 2 into half mv square is nothing but mv square minus work done by spring minus half k into delta L square, where delta L is L naught into 5 by 4. See, sec theta is 5 by 4, and 5 by 4 minus 1 is 1 by 4. So L naught into 1 by 4 whole square plus mg into x, plus mg into, what is the value of x? The value of x is nothing but L naught into 3 by 4. L naught into 3 by 4. Now when you solve this one, so one more thing, we have to replace this k by 5 mg by L naught. No, 5 mg by L naught is given in the question. See, is given in the question. Out of this x was nothing but k. So out here when we solve this one, we'll get, so minus half 5 by L naught, this is not 10, 5 by L naught into mg into L naught by 16 plus 3 mg L naught by 4. Now let me cancel out the m. So I can take m common and cancel it out. Okay, so m is cancelled. Okay, what else can be done? Acha, out here this is L naught square. Okay, not L naught. Why? Because this L naught whole square would become L naught square. No? So this L naught and this square would get cancelled. So L naught and whole square will get cancelled. Okay. Okay. So the remaining parameters are, so minus 5 by 2 g L naught by 16 plus 3 by 4 g L naught, or V square would be minus 5 g L naught by 16 to the 32 plus 3 by 4 G L naught. Now whenever you add these two, see, the better way of adding these two is, outer denominator is 32, so into 8 into 8, so 8 4 is a 32, so I'll make this 32, and numerator also have to multiply by 8, so 8 3 is a 24, so 24 by 32, so V square is equals to minus 5 G L naught plus 24 G L naught by 32, or V would be under root of 24 minus 5 is nothing but 19 G L naught by 32. So the velocity of the block when it will just break the contact from the surface is nothing but 19 G into L naught by 32. Okay.